Okay, on to the next step, Descartes' rule of signs. Let's do a quick recap. Remainder theorem and synthetic substitution lets you evaluate functions very quickly. The factor theorem says, hey, if you evaluate those functions using synthetic substitution and you get a remainder of 0, you just found a factor. And that was pretty easy. When you're looking at the problem and getting started, the fundamental theorem of algebra and its corollary says, hey, do you see the degree? That's how many solutions there are. Descartes' rule of sign is kind of neat because what it does, it says, hey, take any polynomial. I got a couple rules here, and I'll explain these rules here when we do the example. But basically, you're going to be able to tell me how many positive roots there are. You'll be able to tell me how many negative roots there are. And you'll be able to tell me how many complex roots there are, which is pretty handy if you know how many there are. Why? Let's say I'm guessing and checking and trying to find a bunch of roots, and I've done the Descartes rule of signs, and the Descartes rule of signs told me there's going to be one negative root. Well, if I find a negative number that's a root, uh, I'm not going to ever look at any more negative numbers because there was only supposed to be one of them. Let's say they told me that there's going to be two positive roots. Let's say I'm guessing and checking from all the numbers that I've found a positive root. Well, I know there's going to be one more, so I can keep checking my positives. All right. So that's the idea behind the thing is it helps you plan your attack by knowing how many of the different kinds of roots you're going to have. That way you know when to stop looking or when to keep looking for different kinds of roots. All right. Now, how do you actually use Descartes' rule of signs? There's two parts to it. You can see there's the two bullet points here. We're going to do the first one. Uh, we're going to look at the function, and the positive real zeros, or positive roots, is equal to the number of changes of sign of the function. Now, that means each term, whether it's switching from positive to negative. Let's do that real quick on this problem right here. So, I got my function f of x equals x to the 6th plus 3x to the 5th minus 4x to the 4th minus 6x cubed plus x squared minus 8x plus 5. Now, first off, I can use the fundamental theorem of algebra to tell me, hey, how many roots are there? The degree is 6, so there should be 6 roots. Up next, I take a look at each term. X to the 6 is positive. Plus 3x to the 5th. No sign change. But 3x to the 5th is positive, and you can see it changes to a negative on the next one. So there's a change right there. Negative 4 to negative 6, no change. Negative 6 to positive x squared, that's another change. Positive to a negative, that's a change. Negative to a positive, that's a change. So here I can see there are 4 sign changes. So that means there are 4, 2, or 0 positive roots. Now, why did I write if there's 4 sign changes, how come there might be 2 or 0? That's another part of the Descartes rule of sign that I kind of saved there to the end. It's less than this by an even number. So basically, if you count 4 sign changes, there might be as many as 4, but there might just be 2, and there might be 0. So just keep that in mind as you're doing it. You could look through all the positive numbers and never find anything, even though we got 4 sign changes here. Not very likely, but it's possible. Okay, the next one is the tricky one. The number of negative zeros. So now we're looking for the negative numbers of this function. It's the number of sign changes again, but this time we have to plug in p of negative x, and that's where it gets tricky. So I'm going to take my function f of x, and everywhere I see an x, I'm going to plug in a negative x. So let me just write it down real quick here. To the 6 plus 3 times x to to the fifth minus 4x to the fourth minus 6x cubed plus x squared minus 8x plus 5. So everywhere there's an x, instead of there being an x, I could have a negative x. Okay. Now, the nice thing about this is it's not as hard to figure out what changes as you think it would be. If you have an even power, the sign stays the same. For example, x negative, well, I'll just do it with a number instead of with an x here. How about what's negative 3 squared? Well, that would just be 9. It didn't matter that it was a negative 3, whether it's a positive 3 being squared or a negative 3 being squared, it's still positive 9. If it is an odd power, the sign changes. So, how does that work? Well, negative 3 to the third is negative 27, and positive 3 to the third is just positive 27. So you can see there's a difference in the sign change there. Now, what does that mean for rewriting the function? It actually means I can skip this step of having to show to plug it all in. What I can do is, and this is where I wish I had another finger where I could point at the screen. The first term, x to the 6, is an even term. Keep it exactly the same. The next one is an odd, x to the 5th. So since it's an odd power, the sign is going to change. So that instead of saying plus 3, I'm going to say minus 3, x to the 5th. And fourth degree polynomial, or fourth degree term, stays the same. So it stays negative 4x to the 4th. The next one changes. Negative 6 to the negative x cubed becomes positive 6x cubed. X squared, no change. And then we have negative x times negative 8. That would be positive 8x plus 5. So I'm going to highlight here the ones that changed. Odd, odd, odd power. So you don't have to write down everything. You don't have to show everything getting plugged in like we did. Just change the odd powers. Just change their sign. That's all you need to do. But then you go through the same thing, and now we're going to notice the changes. And this time we'll see it starts positive, goes to a negative, negative to a negative, negative to a positive, 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 positive. So here there are only 2 or 0 negative roots. Okay, now here's the big thing that comes from this. We know how many positive roots there are, we know how many negative roots there are, but I said it also told us how many complex roots there were. Well, that's because we know there's going to be 6 roots from the fundamental theorem of algebra. The way I like to show this is I like to make a little chart. I have positive roots, I have negative roots, and I have complex roots. And I like to go through and process everything together. I start with 4 positive roots. And if I have 4 positives, I could have 2 negative roots, and the total number of roots I have is 6, so I'm done. Because remember, I have to have 6 roots. I could also have 4 positive roots, but on the next time around, maybe I don't have any negative roots. Well, right now, 4 plus 0 is just 4. I don't have all 6 of the roots, so the other 2 roots must be complex numbers. Now I've gone through all the possibilities of the positive roots, so now I'm going to go, where for 4, I'm going to go to 2 positive roots, 2 negative roots. I only have 4 so far, so I need another 2 for the complex. Continue on, 2 positives, 0 negatives. That means 4 of the roots have to be in the complex. And we do the same thing here with 0 positives, 2 negatives, 4 have to be in the complex, 0 positives, 0 negatives, all 6 of them are in the complex. Now, this bottom half, this is dangerous. Usually We don't have methods to find four um, uh, complex roots or higher. Two is usually about the best we can do, but we can do. The big thing here is now we have a map. This is a map of potential roots. I think potential just has one T in it there. Potential roots. We know how they're going to be paired up. All right, we're going to use this later in our planning.